when we looked at fitting a regression line to a set of data, the scenario that we were looking at looked like the graph on the left, where we had a scatter of data points, and then we were trying to find the best fit line for those data. But I want to think about a specific context in which there are a set of known input x values, and they're listed here. And then for each x, we're going to think about there being a distribution of y values around a mean. So the blue points represent that there's going to be some varied y values around a red point that's the mean. And so there's a best fit line that goes through the data as so, but every single input x value has its own distribution of y values around those means. So in what context may you have seen this before? Well, let's think about how weights may depend on heights. And so we're going to consider a fictitious population of adult men below. And in this population, we see that the heights are going to increase, and so the weights are going to increase accordingly. And so for every height, say 72 inches, there's going to be a normal distribution of weights around the mean. So the average weight for a height of 72 inches is 161 pounds, but not every person who is 72 inches tall weighs 161 pounds. There's going to be some variance of weights. And so we're going to allow them to vary using a normal distribution. As you increase the height, we expect on average for weights to increase. And so if you increase the height to 76 inches, we expect that the average weight would be 178 pounds. Okay, but then again, there's going to be a normal distribution of weights around that average. Some people are going to be heavier for that height of 76 inches. Some people are going to be lighter. And so when we're thinking about data that is linear, we're going to assume that for each individual input, in this case height, there's going to be an average for my output, which in this case is weight, but then there's going to be a normal distribution around the average. So let's move into talking about linear models. So here we're going to let x be the height and y be the weight of a population of adult males. For each height, x, there's going to be a normal distribution of weights. Y, and that normal distribution is going to have a mean. The mean is going to be mu y given x. So that's going to be the mean weight of men who are x inches tall. So the mean is not going to be one individual point. The mean is going to be dependent on what the input height is. There's also, because we're going to have a normal distribution of weights around that mean, there's going to be a standard deviation, sigma, and sigma of y given x is going to be the standard deviation of weights of men who are x inches tall. And then if certain conditions are met, we're going to think of y as having a distribution that depends on x. So we're going to think about our weights as having a distribution that depends on heights. Okay, and so what are some properties of the linear model? So first of all, there's the idea of linearity. Okay, y is going to be a mean weight given a specific height, plus there's going to be some randomness around that mean. There's going to be a normal distribution around that mean. But that mean of y given x is going to be a linear function of x. In other words, the mean is going to be some intercept, I'm going to call that beta 0, to represent kind of the true intercept for that population. And then a slope, I'm going to call that beta 1 to represent the true slope for that population times x. Okay, so the mean is going to be a linear function, in this case of heights. So that our linear model says that every weight, y, is going to be the mean, which is a linear function of height, plus some randomness that goes around the mean. So in other words, there's a normal distribution that goes around that mean. And then the second property of the linear model would be that there's going to be constant standard deviation, that sigma of y given x actually doesn't depend on x at all, that it's going to be constant, and we'll call that constant epsilon. Now, what does this epsilon represent? Well, it represents the random error. And it reflects the fact that y, which in this case is weight, can vary for any fixed x. So the epsilon represents the fact that some people who are tall might be lighter and some people who are tall might be heavier. There's a normal distribution of weights around a particular height. So we can see that in the picture again here, where we have for every height a normal distribution of weights around that height. Okay, we'll note that for this model, where we've given some weights for every height, that the standard deviation is constant at 20. Now, the conditions of this being represented by a linear model are saying that we should have a mean and a standard deviation for this model. Okay, so what is the mean? The mean is going to be, again, beta 0 plus beta 1 times x. And then sigma is supposed to be constant, so that's supposed to be 20. Okay, so what are the intercept and slope for this particular model? Well, the intercept, or the slope, I can figure out by kind of recognizing that in this data, that there's a 4-inch spread between each of my heights, and there seems to be a 17-inch or 17-pound spread between each of my weights, right? So my slope, my beta 1, which is the slope, is going to be 17 pounds per 4 inches, or 4.25 pounds per inch. Okay, now how do I find my intercept? Well, my intercept, which is beta 0, should be a y value minus beta 1 times x, if I kind of just solve for beta 0. So in our case, I'll just pick a y value. Let's just pick 161 pounds, which corresponds to 72 inches. And so that will give me an intercept of minus 145. So I'm going to go ahead and write those values in here. They're going to be minus 145 plus 4.25 times x. Now you'll note that this model is going to be good for, say, predicting values that are in between my data points. So I could say like, oh, what if I have somebody that's 70 inches tall, what's their average weight going to be? It's going to be minus 145 plus 4.25 times 70. And so somebody who's 70 inches tall will weigh 152.5 pounds on average. Okay, but this model will start to break down as we get farther away from our data. So for example, if you were to plug in 0, it would say someone who is 0 inches tall weighs minus 145 pounds, which doesn't really make all that much sense. Okay, so with these two pieces, I can write down what my general linear model is. And my general linear model is going to be my intercept minus 145 plus 4.25 pounds times x plus epsilon, where epsilon is kind of my randomness. Okay, so what is epsilon? It's a normally distributed random variable with mean 0. And we'll make sigma going to be my standard deviation. And that sigma, of course, is going to be constant.